One of the great things about ice cores is that they record information about ancient climates. In particular, ice cores are the only archive from which we can directly obtain records of past atmospheric composition. And this is possible thanks to small bubbles which become trapped inside the ice during the transition of snow to ice. Unlike ice cubes that we use in our drinks at home, polar ice sheets almost never form from the freezing of liquid water. Instead, they form from the building up of snowfall over thousands to millions of years. Once snowflakes fall onto the surface of an ice sheet, they begin to deform and merge with neighboring snowflakes to form grains. When the next snowfall event happens, the older snow becomes buried, and the weight of the new snow layer compresses the buried snow by forcing the air in the space between the grains to return to the surface. This buried snow is called firn and is compacted snow full of channels of air called pores. The air in the pores of polar firn is really an extension of the surface atmosphere. For example, when the snow is getting older with depth, the air in the pores is still connected to the surface and can be thought of as the same age as the surface snow and overlying atmosphere. At around 50 to 120 meters below the surface, however, the firn becomes so compacted that channels linking the pores to the atmosphere become cut off, trapping them as bubbles within the ice. These bubbles now hold a sample of the atmosphere. This process is called bubble trapping and is a complex mechanism that influences how we interpret ice core records. One of the key challenges of interpreting ice core records is that the age of the gas is always slightly younger than the age of the surrounding ice. The ice age is the number of years since the ice was at the surface of the ice sheet, while the gas age is the number of years since the gas was sealed off from the atmosphere. We are trying to improve our understanding of the entire evolution from snow to ice so that we can have the most accurately dated gas and ice records. This is really important to improve our understanding of Earth's system, such as the relationship between carbon dioxide and temperature, and how this has changed in the past. I'm part of the Deep Ice Project because I am fascinated by the way ice sheets drive and respond to climatic changes throughout Earth's history.